Hello and welcome to lecture 17 of the course Theory of Computation. In the previous week, week 3, the last lecture of week 3, we started seeing context-free grammars, right? So we saw the definition, we saw some examples, and we even saw the definition of ambiguity, like what it means to be for a grammar to be ambiguous. In this lecture, we are going to see a specific form or a structure for the context-free grammar, which is called as Chomsky Normal Form. So this was invented by Noam Chomsky in, I think, late 50s. So this gives a certain structure to the Chomsky context-free grammar, right? So context-free grammar, as we know, like it's a set of rules where each variable gives rise to multiple derivations, right? So it's a bunch of rules, right? So and we want to know what are the strings that we can form out of this grammar, right? Right. So let's see why we need such a structured set of rules, which is the Chomsky normal form, right? So as I said, this is a standardized form. So already the definition for the context-free grammar gives some standards. So here we are going to be imposing more structure than what is insisted by the definition of the context-free grammar, right? So to make it easier to motivate this, let's see what is the main goal of a context-free grammar, right? So, or what is one of the things that we need to do with it? So one of the things, think of a grammar generating, let's say, all strings which are like in the syntax of a programming language, and the computer has to actually read the string and interpret it, right? So it has to understand it has to break down the structure and try to interpret the structure of the string and see what this really means, that one line of the code or whatever, right? So it has to be able to understand how the string was derived by the grammar, right? So this is one of the main goals of what we want to do, or what one should be aiming to do with a context-free grammar. So they should be able to understand how, like whether a string W is generated by a grammar, and if it is generated, how is the generation, right? How exactly is it derived, right? So this is one of the things that we want to do, and the rules should be in such a way that it should enable these kind of like questions, right? So it should be easy to check whether the string W is derived from the grammar, and if so, how it is derived, right? So we'll briefly illustrate how in general context-free grammar it may not be that easy, and how the Chomsky normal form makes it somewhat easier, right? So consider this particular the context-free grammar that is there in the bottom of the screen. Like S gives 0 S1 and 1 S0 S1 and T, 3 different rules for S, and T gives S or epsilon. So there are a couple of issues here. So let's say we get a string, let's say 1 0 1 0 0 0 something, right? So it's a string of length 7. So now one possibility of trying to check whether this string is derived from this language or this grammar is to actually try out all possible derivations of length of a certain length, right? So you try out like you basically try out all the rules, and kind of it may come out as like a tree, and see whether like what are the strings of length 2, then 3, length 4, and so on, and once you reach length 7, you see whether this particular string 1 0 1 0 0 1 0 1 0 0 0 0, whether this string is derived from this particular grammar or not. And if basically you may also have other strings which may have 1 0 S 0 1 T, some other strings may be there that are of length 7 which have variables in them, but the point is that it is enough to consider all strings up to length 7, right? But then the issue is that it would have been fine if the lengths of the strings that are derived do not become smaller, right? When you apply rules, if the lengths of the string only keep getting bigger, I can stop at a certain length, which is the length of the string that we want. But in this particular grammar, that is not the case, because we have a certain rule here. We have a rule that T gives epsilon. So potentially I could have a string like this 10s 10t00, and in the next step this T could go to epsilon and I could get this 10s100, right? And even this S can go to T and then T can go to epsilon. So the next step I could get this. So the string can become smaller. So this is why the rules that derive empty strings, right? So the rules like this, T gives epsilon, this is not desirable. Another issue is that in any program, we don't like loops. Loops meaning A gives B and B goes back to A, right? So some kind of infinite loops. And that sort of a thing is happening here. If you see, there is S gives T, right? And T gives S. So when you are trying to structurally bring down all possible derivations, this can possibly create problems. So even now I am not really explaining a proper algorithm, but I am explaining issues that are likely to arise when we try to develop an algorithm, right? So S gives T and T gives S can result in problems. So empty derivations I already explained, and this is a loop. And one way to remove loop is to not allow like single derivations, meaning derivations like one variable giving another. So this is why one variable giving another we don't want. And there is also this thing called useless rules. So some useless meaning, what if some rule is never actually used in generating a string? Right? Some rules are there, but it never, if you try to use that rule, it never ends in the we never get an actual string by applying such rules. So these are kind of undesirable things, and what we want is a grammar that enables the creation of an algorithm, right? So that is the brief motivation of why we would like more structure. And with this brief example, I hope it's clear why in general the structure of context free grammar is not strong enough to ensure such an algorithm. So that is the motivation for Chomsky normal form. So what is Chomsky normal form? It is a grammar, and the grammar is said to be in Chomsky normal form if every rule is in one of the following types, right? So what is the following types? One is A gives BC and the other is A gives small a. So A gives BC means one variable giving rise to deriving two variables, right? So A gives BC. And the second is that one variable giving rise to single terminal. Okay, so A here is a single terminal, right? And there are two more things that we want. We don't want the start variable to appear in the right side of any rule. So B and C should not be the start variable. We also do not want empty rules. So any rule of the form A gives empty string is not allowed. The only exception is that if we never allow A gives empty string, what if the language that we are trying to create also has the empty string, right? So we want to somehow account for that. So if the language that we are trying to create has the empty string, we allow one exception for this empty string rule. We allow the start variable giving empty string, but not for any other variables, right? So basically the entire CFG is such that of this rules of this type, A gives BC or A gives small a. So B and C cannot be the start variable, and epsilon does not feature in the right hand side of any rule except possibly start gives empty string, right? So this is the structure. A gives BC, A gives small a, and where A is a variable, B and C are variables which are not the start variable, and if needed we allow start gives empty string. We do not allow another variable giving empty string. So if the entire context free grammar consists of only rules like this of this type, we say that the context free grammar is in the Chomsky normal form, right? So one of the advantages is that now you can see, let's say you can see that every variable, now we apply the first type of rule, right? A gives BC, the length of the resulting string increases by 1, right? So maybe you have things like A gives BC, now maybe B gives something like, let's say CD is there. So every time you apply the a rule of the first type, the length of the resulting string increases. If you apply the rule of the second type, let's say C gives small c or something, the length does not change. And it is not that difficult to see that to get from a, so now maybe see that the small capital D gives, let's say, small a, and capital C gives small c, right. So now if you can see from the start variable a to get a string of length 3, we use 1 2 3 4 5 steps, 1 2 3 4 5. So this is something that is easy to see, which I'll ask you to show as an exercise. That is that any string requires exactly 2n minus 1 steps for the derivation. Okay, so a string of length n, okay, so maybe I missed to write, of a string of length n requires exactly 2n minus 1 steps in its derivation. It's easy to see because first, from the start variable to go to a string of variables of length n, we need to do n minus 1 steps, and then we have a variable of, there is a string of n variables, and each one needs to be replaced, so another n steps. So that's pretty much the proof, but I leave it to you to formally reason it. So there is a predictability. The point is that it is not like if you come a certain way, or a certain string can be derived in 3 steps, but another string of the same length requires 10 steps. So now we know if there is a string of length 5, it requires exactly 9 steps, whichever way you take. Any string of length 10 requires exactly 19 steps, right? So this is some kind of structure and order that we are getting as a result of the structure imposed by the Chomsky normal form. And another thing that we will see very shortly, maybe not, maybe in the next lecture, is that because of the structure, we are able to have get a algorithm that is able to check whether a string is generated by a grammar. Okay, so there is an efficient algorithm. This is called the CYK algorithm, which we will see in the next lecture. Right. So this is all good things about the Chomsky normal form. Right. So the natural question that one may ask at this stage is, okay, so I agree things are good, that we have all this structure, but what if I have a grammar that cannot be put in this structure, right? So maybe is the structure too rigid that it is not general, right? That's a natural question that one may ask. The answer is, interestingly, that it is not too rigid, and that you give me any context-free grammar, I can convert it into a grammar in the Chomsky normal form. So any context-free language can be written as a context represented by a context-free grammar in the Chomsky normal form. Right? Any context-free grammar or any context-free language is generated by a grammar in the Chomsky normal form. So, okay, so so we'll get into the proof. The proof is fairly like direct, in the sense that it gives us a process by which how we can convert any context-free grammar into the Chomsky normal form. So I'll briefly go over the process, and instead of just explaining the process, we'll go through a example. Okay. So what is the process? So there is an optional step which will not which we'll just briefly touch upon. So first is to remove useless symbols and productions. So what do I mean by that? So suppose this is the grammar. Okay, the grammar is this, right, the one in the box, right. So this grammar, if you see, it's S gives AB and A gives small a. So if you see that the variable B is never used here. So in the sense that there is nothing defined for what the variable B yields. So if you use the rule S gives AB, there is no real next step to go, right. So the B is a useless variable here, right. So B is a useless variable. So we may as well remove the rule as well, right. S gives AB, right. So this is an example of a very simple grammar where there is a useless rule or useless variable, right. Anyway, so this is one example. So the first step is to remove useless rules and variables. This is an optional step. This is not required for the rest of the process. So that's why I'm saying it's an optional step. So just to remind ourselves, what is Chomsky normal form? Every rule should be of the form A gives BC, where B and C are not the start variable, or A gives small a, where A is a terminal. Small a is a terminal, right? And we are not allowed to have epsilon feature in the right hand side of any rule, except start variable gives epsilon. So the first thing to tackle is there may be maybe I have the proof written here, but I will not go through the proof. Instead, we will work an example, right? So suppose that may be more illustrative. Right? Suppose this is the CFG, right? S gives TST AB, T gives B and S, and B gives small b and epsilon. So there are three variables, capital S, capital T and capital B, two terminals, small a and small b, right? So there are many violations here. So first of all, there are rules like this, TS, like the rules where right hand side has three variables and right hand side has a variable and a terminal, a comma b, a small a capital B. There are rules T gives B, right, which is the rule where the right hand side has a single variable. There are epsilon rules, that is B gives epsilon, and the right hand side also has start variable, S gives TST and T gives S, right. So there are many kinds of violations. So we will see how to fix all of this, right. So we want all the rules to be of the form S gives A gives BC, where B and C are variables, and A gives small a. So the first thing to do is, so we don't want the start variable on the right side. So the simplest way to handle that is to just introduce a new start variable. So we will add S0 as a new start variable, and in order to now connect that with the rest of the grammar, we will just add a new rule, S0 gives S, S0 gives S. So now we have modified the grammar by adding a new start variable, but the grammar is equivalent. So if you see, we will keep the grammar equivalent, we will modify it, but we will ensure that the set of strings generated by the grammar does not change. Right. So we'll keep restructuring it, but we'll ensure equivalence at all stages. Okay. So we added this. So now we have the other violations still. We have rules where three variables are on the right side. We have one variable on the right side, variable terminal combined on the right side, right? But we do not have start variable on the right side. So that is one thing fixed. Now let us try to eliminate the epsilon rules. So we have one rule here, B gives empty string, right? So first let us remove that, right? So I have not written it down, but let's try to work it out. So this is the rule. So what we will do is, whenever B appears in the right side, so we have the rule S0 gives S, let that be, and whenever B appears in the right side, for instance here, we will also include what will happen if so there will be two places where B appears, right? So here as well as here. So we'll also, so by eliminating this epsilon, the epsilon over here, for eliminating this, we'll also try to ensure that the grammar does not, or the set of strings does not change. So let us see what I mean by that. So I have the rule S gives TST, which is unchanged. Now S gives AB is there, but we know that B could have gone to epsilon, but now we are removing that, right? So which means we account for it here by allowing. So what would happen if b goes to epsilon? So we take that in this stage itself. So if b went to epsilon, this ab would have been just small a. So we just add a rule small a to kind of take into account the effect of what would happen if b goes to epsilon, right. Similarly, we have the rule t gives b and s. So now if b went to epsilon, this entire thing would also go to epsilon. So we add t gives to epsilon and s remains unchanged, and then b goes to, now b goes to epsilon can be removed, because wherever b appeared in the right hand side, we already took into account, took care of what would happen if b went to epsilon, and we have updated. So this is the updated set of rule. So here we have a b in the right hand side, and the possibilities when b went to epsilon were this had to be replaced by small a, and here we had b itself. So b has to be retained, and then we also added when b goes to epsilon, this has to be epsilon. So now we have successfully removed b goes to epsilon, but we have now generated or we have created a new issue. We have this epsilon now, and we have created a new epsilon rule. So now that would mean that I have to take into account, I have to remove this, and there is only one place where t appears in the right hand side, which is this tst, and I have to modify this rule so that this epsilon that appears in the right hand side has to be, so we want to remove this t gives epsilon. So what are the possibilities when t goes to epsilon? So this particular rule has two t's in the right hand side, right, t, and we have to account for all the possibilities. What if both of them go to epsilon? What if one of them goes to epsilon, right? So the modification that we need to do is, right, so we need to remove, we are going to remove this t gives epsilon. So S0 gives S, which is standard, and then S gives, maybe I'll just move it to, S gives, right. So we have TST. Now we want to, we are removing t goes to epsilon. So multiple things are possible. The first t could go to epsilon, which would give us ST. The second t could go to epsilon, which would give us TS. Maybe both t's could go to epsilon, which would give us just S. Then we have AB, and then we have A, and then t gives B and S, and then B gives small b. So now we have we have removed t gives epsilon, and whatever impact the grammar had because of that removal, that we have taken into account by modifying the rules for S, right. So we added new rules here in order to absorb the impact of the removal of t gives epsilon. So this is good now. We have now removed epsilon rules. So we have now two things that are taken care. We do not have start variable in the right side. We also do not have any epsilon rules, right. There are other things that are still there. For instance, we have these unit rules. We have t gives b, which we don't want, right. We have small rules like this, t gives b. We have long rules like this, s gives tst, and we also have rules like s gives small a capital B, which are not in the structure. So the next goal is to address these anomalies, right. So so what are the unit rules? Let's see. So maybe the first thing I have already filled out. So the first unit rule is S0 gives S, right. This is a unit rule which is not allowed as per the rules of the Chomsky normal form. So what we do is S0 gives S, and then S could give all these things like TST, EST, TS, etc. Before getting there, let me just make one more statement. So notice that we have one kind of redundant rule here. We have S gives S here, right. So this is a redundant rule because it doesn't do anything, right, to any grammar. S gives S, it's not even a valid, like there's no change, right? So we'll remove that, can be removed. Okay, now coming back to this removal of unit rule. So S0 gives S is what we want to remove, right? So when we want to remove this, so instead what we'll do is whatever S can yield, we'll just add that to the productions of S0. So we'll remove S0 gives S, but S could give TST, ST, TS, A and AB and A, right? So now that's what we are doing here. S0 also now gives TST, TS, ST. Okay, the order is changed, ST and TS, but it's the same. AB and small a. S also gives the same things, right? T gives B and S, and B gives small b. So while we removed S0 gives S, whatever we could get as a result of that, right? Whatever S could produce, that we put on the right hand side of S0, right? So next thing is T gives B. So T gives B here. Now what would it mean? What would it mean? T gives B. So now what are the things that capital B produces? So that rule, what we'll do is we'll replace this rule, right? We'll replace this rule with whatever small b can produce, which is that small b, we'll remove T gives capital B and we get this. But then the next thing that needs to be addressed is T gives S, right? T gives S. So, but what all T gives S? S can yield. S can yield all this TST, ST, AB, all that. So we need to add that as well, right? So now we modify this into T gives. So let me list down all the outcomes of what T can give, what S can give into T. TST, TS, ST, AB, A, and this B also we need to include, right? This particular B. So we include that. So now that's a result of two. So now this circle rule has to be replaced by this. Everything else is done. So now let me just yeah. So this is the entire set of grammar. S0 gives TST, TS, ST, A, B, and small a. S gives TST, TS, ST, A, B, and small a. T gives this one TST, TS, ST, A, B, small a, and small b. Maybe what I'll do is I'll just sorry, I'll just erase and write the whole thing again. Maybe it's easier if we see the rules at one place. S0 gives TST, TS, ST, AB, and small a. S gives the same thing. And finally, we have B gives small b. So this is the entire grammar now. S0 gives this. So now we have taken care of start variable not appearing in the right side. We have taken care of rules that are deriving the empty string. We have also taken care of rules where of the type A gives B, where A and B are variables. So where exactly one variable is produced. Now the only other issue that we have are one which are rules which are producing more than two variables or not of the proper form. So one variable and one terminal, right? Things like that, right? So this what we do is, now this is also not in the structure of the Chomsky normal form. So what we will do is we will introduce new variables. So whenever three variables are produced, like t gives tst, we will add an intermediate step so that it will first it will derive two variables and then derive three variables. So by introducing new variables, we will restructure this. So this is what we have. So let's see what we do. So so we will introduce two new variables. One is z, which we want to stand in for ts, and then capital A, which we want to stand in for small a, because basically we want to, this is something that we have problem with tst, and this is something that we have problem with ab. So let's see how we fix that. Okay, so s gives, so instead of tst I will say zt. Okay, ts will remain as it is because it is in the form. St will also remain as it is. Now small ab I will write it as ab, and small a is also allowed. So this is what we do. And similarly, so this is s0. Similarly, s also we do the same thing. Right? T also we do the same thing. For T we have one more rule. And now this we have to formalize this particular thing that I said here. Ts gives z, or so we want z to stand in for this ts, right? So we have this new rule, z gives ts, and we have this other rule that a gives small a. So now you see that now whatever modifications we did, S0 gives TST, etc. Now everything is still derivable from this with this change, right? The only thing that is remaining that is not included is B gives small b. So we have written that, and now that completes the transformation. So now if you see, there are no epsilon rules. Start variable is not in the right hand side. There are no unit rules, meaning rules of the type S gives T or something like that. There are no rules where other structures appear. Long, like all the rules are the form A gives BC or T gives AB. One variable gives two different variables or two variables, or of the form A gives small a, where one variable gives a terminal. And you can verify that, you can go through the changes, go through the modification, and you can indeed verify that whatever string that was produced by the original grammar, which was this, all of this are still produced by the transformed grammar, and whatever was not produced are still not produced. We are not, whatever the resulting grammar that we have is an equivalent grammar. It is kind of evident in the way we went about transforming this grammar. But perhaps if you are confused or if you are unsure, you can still verify this. Basically, whenever we modified a rule, or whenever we removed a rule, we ensure that whatever impact the removal is causing, that is absorbed by some other modification of some other rules. Right? So now the grammar is in Chomsky normal form. The above CFG is in Chomsky normal form, and by construction we have ensured that it is equivalent to the original grammar. So that is basically the kind of sort of constructive proof. I'll also share these notes where first in the proof I actually explained how to do this, but instead of going through the proof, we just went through the constructive procedure, right? So yeah, that's it for this lecture. Basically, we introduced Chomsky normal form, which is standardized form, where the rules are of this two types. Sorry, these two types. A gives BC, where B and C are variables, or A gives small a, where small a is a terminal, right? And in addition, we allow S gives empty string, right? And start variable should not appear on the right hand side. And we showed that this is still general in the sense that any grammar, any context-free grammar can be converted into Chomsky normal form without an equivalent as an equivalent context-free grammar that satisfy these structures. And then the advantage was that this gives a structure, and we promised that we will get an efficient algorithm for deciding whether a string is generated by a grammar if the grammar is in Chomsky normal form, right? So we explained the transformation of how to convert any general grammar into Chomsky normal form, and we said that there is this efficient algorithm. Sorry, this algorithm will be covered in the next lecture. It is called CYK algorithm. It's an algorithm that that uses dynamic programming. So we'll see that in the next lecture. Thank you.